continue with this properties, and let me get this for later. Any questions? No? How does the homework look? Okay? All right. We have seen the first law for a closed system. And as noted actually before, so okay, we saw that first law, which is the conservation of energy. We have a delta kinetic energy, delta potential, plus delta internal energy. Right? These all go together as a delta E in a system. That must be equal to Q minus the W. Right? So in general, if the kinetic energy and the potential energy can be neglected in a system, the result is therefore delta U as Q minus the W. And negative W means the system gives us work or we give the system work.
Give the system work.
The system gives us work. Because this actually W is positive. And this comes out of the system. Q, if Q comes out of the system, Q is negative also. But Q going in is positive. W going in is negative. Negative times negative is positive. Therefore, delta U increases when we add heat or work now to the system. This can then be written as M, because I have a closed system basically. M little u, 2 minus little u1 equal to Q minus the W of the system. Okay, so that's again for a closed system, this chapter. Now, now we look at the specific heats. We define a specific heat at constant pressure. Constant pressure as Cp, lowercase, because we are using specific values now. Cp equal to rate of change of enthalpy with temperature, of course, at constant pressure. And specific heat at constant volume is Cv, partial U with temperature at constant volume. Okay. Therefore, the ratio of the two is called the specific heat ratio. K, Cp over Cv. Okay? And K in general larger than 1, meaning Cp is always larger than Cv. Okay? Any questions? Yes?
Is that meant to be specific enthalpy and specific
internal energy?
Right.
Right. partial H and partial little u, where H is little u plus P, specific volume. Right? Okay. Now, generally, as you see, CP and CP actually, let's put first. Now, CP depends on both pressure P and the temperature T, or in other words, V and T. And then CV depends on V and T, or to that effect, P and T. Okay. Later I'll show you the tables for CP and CV. Yes?
Is that constant volume or constant specific volume?
Yes. A constant specific, where is it? Here?
No, just for the second one. Yeah, right there.
Yes. Constant volume. This indicates that volume must be constant for the rate of change of u with time.
Okay, because I thought the little v was supposed to be specific volume.
It is a specific volume.
Oh.
Yes. Yes. We are now working only with the specific values, okay, per unit mass, everything. Okay. Now, CP and CV data are given in tables A19 in the appendix. A19 to A21, and I'm going to show you these. Remember, I ended the lecture, the previous lecture, with the property approximation for subcooled liquid. Remember, for the liquids, I told you that we can assume the properties at the saturation line for liquids at the same temperature. So let us just expand on that a little bit. This is now property approximation. For liquids. Remember the dome, let's say they're on a TV plot. This is the part of the dome, right? And then let me also draw the rest. So this is a line of constant pressure. Yes? P. You remember that? For liquids, of course, this is the pressure constant line. Imagine you're working with this actually temperature. So practically almost all of the properties at this point can be approximated by the properties at this point on the saturation line, because volume of a liquid practically is constant, even with pressure. Also, energy and everything. So, let me just write the approximate equation as a specific volume at any temperature and pressure for liquids, of course, to the left of this dome, approximately Vf at that temperature. Does it make sense? Property, a specific volume here, almost can be approximated as the specific volume on this F line. And this is the G line, right? And the critical point. Okay. Similarly, U at T and P, approximately UF at that same temperature. Many of the substances, they haven't provided the properties for subcooled liquid for them in the book. So all you need to do is go to the saturation table for those properties or substances, find the value at that temperature. For example, for a specific volume or for the internal energy. Also, I know that since enthalpy H is internal energy plus PV, right? That's the definition of enthalpy. Therefore, I see that H of T and P can be written as approximately U F at the same T plus, by looking at this, pressure Vf at the same temperature. Yes? My handwriting is large enough, big enough, you can see it over there. And then, in an alternate form of this, is that H of T and P approximately HF of T plus Vf for the saturated liquid of T multiplied by P minus P saturation at the same temperature. Why is that? Notice that P saturation at the same temperature is this line. Everybody agrees? P saturation at the same, let's call it T0, is this line. But the pressure does not affect that much the liquid, especially when I have volume involved. So this term can be ignored because of the effect on the specific volume is minimal. Okay, as a result, I see that H, T and P can also be approximated as HF at the same temperature. Okay. So these are the properties that we use for liquid water. We have the table, subcooled liquid, so we can use that. But for any other ones, they have not provided usually methane, ammonia, refrigerants and things like that. So we go directly to BF or VG, or UF or HF. For anything to this side of the dome. Okay. So that is a good approximation usually to use. If a substance can be modeled as incompressible, meaning that therefore density is constant, right? Like liquids. I can now write incompressible substance model. Since specific volume is constant for this situation, therefore U, little u, internal energy, is just U of temperature. Okay. Also, I have Cp equal to Cv. No change, right? Because volume is constant. And we call it, therefore, just C. You may remember from physics that for water, for example, did they ever write for you Q equal to mc delta T?
Yes.
Yeah, it's a very famous heat transfer to water, liquid water. That C is therefore is just a specific heat, which is no at constant temperature or pressure. No at constant volume or the pressure. So this is for an incompressible model. Okay. And then I see that they always have said that CV, rate of change of internal energy with actual temperature, CP, rate of change of enthalpy with temperature. And therefore, for an incompressible model, I can write U2 minus U1 equal to C, T2 minus T1. Also, H2 minus H1 equal to C, T2 minus T1, because that is U2 minus U1, plus what an incompressible substance has a constant specific volume, plus little v T2 minus T1. P2 minus P1. Of course, according to the definition, H equal to U plus P. Yes? Okay. So there is a lot of actually good simplification for an incompressible fluid. But generally, this contribution is generally small. Compared to C times T2 minus T1. Okay. And can be ignored. So you see that U2 minus U1 equal H2 minus H1 for an incompressible in general. Okay. Now comes the introduction for generalized compressibility charts. I'm going to try to be as clear as possible here because sometimes it's a little confusing for the students. So, here let me just need more space also. Generalized compressibility charts. Here we look at the pressure, the specific volume on a molar basis, PVT relationship. We look at PVT relationship. Okay. This drawing is in the book. I'm also going to show it on the screen later. But here we have something called reduced pressure. PR. And on this axis, we have something called Z, where Z is defined as Z equal to P V bar, the specific volume on a molar basis. Volume per mole instead of volume per mass. Bar means now per mole for any property. PV bar divided by R bar T, where of course R bar is the universal gas constant. Okay. This is Z is called the compressibility factor. Z. Then, of course, R bar, universal gas constant. Same value for every gas, equal to 8.314 kilojoule per kilomole degree Kelvin. 8.314. Some of you may not see it if I write actually here, so I write it here. R bar, universal gas constant equal to 8.314 kilojoule per kilomole Kelvin equal to 1.986 BTU, British thermal unit, right? Per pound mole, degree Rankine. For Kelvin, we don't put a degree on it. Okay? But for Rankine, Fahrenheit, Celsius, equal to 1545 foot-pound force per pound mole Rankine. Okay. That's the constant value for every gas. Then PR is defined as the pressure, actual pressure over the critical pressure of that substance. And also TR equal to temperature of the substance divided by critical temperature of it. Okay. You remember the critical values at the top of the dome? Okay. Those are fixed for any particular substance. They have a fixed value. Okay. Now, therefore, here you see that Z is PV bar. We can also easily show that Z, which is PV bar over R bar T, can be written also equal to multiply and divide by the molecular weight. Okay? Therefore, it becomes also PV over RT for the gas, where R is R bar divided by the molecular weight of that substance. Okay? And as you see here, molecular weight is different for different substances, right? Therefore, R is unique to that gas, but different than R for the other gas. But this is common between all of them, R bar. Okay. As a result, you see that V, or actually V bar is molecular weight M. Let me show molecular weight just by a capital M, so that you don't get confused with the W. M, little v. Molecular weight is M. And so, this is an alternative form for Z. Okay. And of course, R bar is Rn. M for the gas. Okay. Now, these are now, let's say 0, 6, 3, 1, 2, 4, 5, and then 0.5, 1.5, 2.5, 3.5, 6.5. Okay. Then Z, let's say 0.1 to 1.1. So .2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. Okay. These are now lines of constant TR. Let's take now this one coming to maybe here like this and then going like that. Generally more straight even. Okay. This is for TR equal to 1. Notice that TR is temperature over T critical. Then TR equal to 1.1. Maybe something like this. 1.1. TR equal to 1.2. 1.3. 1.5. 2. No. These are experimental data that they have done for 10 different substances, and then ironically all of them fall on the same line for these, say, 10 substances. As you see these substances. So those are the experimental data, and they have fitted those lines together. They are, you see that for these, here, all of these points are for methane, then ethylene, ethane, propane, N-butane. These are hydrocarbons, right? And etc. Also, let's actually complete it. Isopentane, and N-heptane, nitrogen, the carbon dioxide, and water. Absolutely no relationship on the family-wise, to each other, right? Water has nothing to do with, for example, nitrogen or CO2. So you see how fascinating this chart fits practically material substances that are totally unrelated to each other. These are not gases, of course, right? Some of these are, okay, some of these are liquid, right? But all of them fit this type of a behavior, especially for the, let's say, temperature divided by their critical temperature. They all fall on the same line for TR equal 1, for TR equal 1.1, 1.2, etc. Okay. Therefore, that's why we call it a generalized compressibility chart for a bunch of substances, and any other substance fits also this. Yes?
What does the bar above the specific volume mean?
The specific volume, it means per mole,
Okay.
molar, right? Not per mass.
Thank you.
Sure. In this book, Anything with a bar means on a molar basis. Okay. Now, notice that with this curve fit then, something interesting actually happens here now. For each specified value of TR, oh, by the way, this is 2. Okay. For each specified value of TR, you see that the compressibility factor Z approaches 1 when PR approaches 0. Right? This is a very important actually point here. Why is that? Because if Z is 1, I get the ideal gas law, right? For Z equal to 1, PV equal to RT. Fine? Therefore, but this does not really mean that the pressure must be 0 to make P over PR. Actually, no, to make P over P critical 0, right? Not necessarily I must have a pressure of the gas equal 0 to be here and the substance obeying the ideal gas law 1 equal to PV over RT. This is for the ideal gas law. Right? You see that for Z equal to 1. So they all approach the ideal gas behavior if the pressure goes to 0. But as an example, you don't need this, right? So, what I mean here is that, first of all, low values of PR reduced pressure, right? Where Z is approximately 1, do not necessarily correspond to ranges of low absolute pressure, which is the pressure P, of course. Example. In order to justify this, let's say PR, if PR equal to 0.05, which is very small, yes? It's 5% of the critical pressure. P is 0.05 P critical of that substance, of course. Using table A1 in the appendix, which I'm going to show you. Using table A1 for PC values, we see that for water vapor. The table shows PC is 220.9 bar, right? Approximately 220 atmospheres. 1 bar is approximately 1 atmosphere. From this relationship that we assume 0.05, I see that pressure is what? 11 bar. 11 atmospheres. That's not near zero, right? Ammonia, by not near zero, I mean it is just a tiny fraction of the critical pressure, yes? It is 0.05. But still it's 11 atmospheres for this water vapor, which is not even a gas. Okay. Ammonia. PC is 112.8 bar. This gives me pressure of 5.6 bar. Substantial, almost 6 atmospheres. That's a lot of pressure. Okay. Carbon dioxide. PC 73.9 bar. That gives me pressure of 3.7 bar. And air, which is a combination of H2 and O2 and N2, and we can treat it just as a single gas. Okay. PC 27.7 bar, giving pressure 1.9 bar, practically 2 atmospheres. Therefore, they range from 2 atmospheres to 11 atmospheres, only with 5% of their critical values. As a result, you see that these are not in practice considered as low pressure, right? Yet, Z approaches 1. And therefore, we are here. So, not only for gases, I can assume the ideal gas law, right? But if a substance deviates from ideal gas behavior, instead of this, I can use this to practically, and I made no approximation in here, okay, regarding low pressure or actually anything like that. So this compressibility chart shows us what? The direct relationship between volume, pressure, and the temperature of any substance that you have here. Okay? From this, if you know the pressure and the specific volume, you can find the temperature of the gas or that substance. Okay? This is kind of a generalization of the ideal gas law. Okay. So the generalized compressibility charts here, they show that at states where the pressure is small relative to the critical pressure, right? At states where the pressure is small relative to the critical pressure, then the compressibility factor Z is approximately 1. So for example, for butane, if its pressure is much less than its critical pressure, I can treat it as a Z approximately 1. Okay? And so, at such a states, we can assume with reasonable accuracy that Z is approximately 1, and therefore PV equal to RT for that substance. But we call this relationship ideal gas law. All gases obey practically this law. Okay? Some vapors also do, as you see here. Okay. So, therefore, this generalization you can find now, for example, knowing the temperature and the pressure, you can find the Z for that substance, right? Let's say you have, I don't know, isopentane. You know it's PC and TC. You come here, you go here, you find that it's here. You go here, you find it's Z. Yes? Substitute in here. You find its specific volume at that state. Okay? Not only that, but the ideal gas law by itself is just another important thing that we use all over the place. For air, for methane, for even methane sometimes. For air, for CO2, for nitrogen, and things like that, we can use directly PV equal RT. Yes?
Just to confirm what you were saying earlier, so if the PC is a lot lower than the PR, then we assume the Z to be 1, or is it the other way around?
It's the other way around. If PR is just a fraction of PC,
Okay. Thank
which
you.
is what, because as you see, PR is P over PC, right? PR being 0.01 means pressure is 1% of the critical pressure.
Thank you.
Sure. It may not be low. Why is that? Because for water vapor, if it's 0.01, right? This is what? Approximately 2 bar, right? 1/5 of this. 2 bar is not low. Low pressure at all.
Okay.
2 atmospheres, but yet you can use Z equal to 1.
Thank you.
Sure. Alternate forms of the ideal gas law. So now we look at the ideal gas model based on what we have seen as a generalization, generalized compressibility of any material. The ideal gas model. So we saw that PV equal to RT. But I know that what little v is V over mass. Yes? Therefore, another version of it, PV equal to MRT. Another form. Since little v is V bar divided by the molecular weight, yes, and R is R bar over molecular weight. Therefore, we have also PV bar is R bar T and with V bar being what? Volume divided by number of moles, right? N number of moles, little n. I see that PV equal to N number of moles R bar T. So different forms of the ideal gas law. All the same practical. Now we look at the ideal gas model. 20 minutes. Let me just, to be on the safe side, I'll keep this. So, here, therefore, I'm following this ideal gas model. Now, for an ideal gas, then it can be very comfortably assumed that U is only function of temperature. Also, since H, which is U plus PV, yes, equal to what then? U function of temperature plus, but PV is RT, right? Plus RT. Therefore, H is also function of temperature. Okay. If the gases obey this model that I've shown here, PV equal RT for an ideal gas. Therefore, we also can show that the specific internal energy function of temperature only. Therefore, CV, which is partial U with temperature at constant specific volume, yes, can now be approximated as just du by dt. Because U is only function of temperature, yes? So, for a dependent variable on one independent variable only, I can write the partial derivative as an ordinary differential, right? Because U is only function of temperature and not function of temperature and pressure. Therefore, I can write it as du by dt. This is for an ideal gas. In addition, upon integration, integrate, and we see that from this I have U. Okay, let me write it du equal to CV dt. Yes? And so I see that U at state T2, U of T2 minus U of temperature T1 for the temperature T1 of the substance is therefore equal to integral from T1 to T2 of CV of T, of course, dt. A very important relationship for an ideal gas. I can find the change in the internal energy of a gas by integrating its specific heat at constant volume with respect to temperature. Yes?
For the specific heat, just to clarify, the lowercase t, is it temperature or time?
Oh, yeah. Sorry. Sorry. Okay. Thank you. dt. This is a relationship for an ideal gas. Also, I have, as we saw before, therefore, Cp for an ideal gas, which is partial H with temperature at constant pressure, becomes therefore dH by d temperature. Yes? Very good. And so, according to this, therefore, for ideal gas, as a result, I see that H at temperature T2 minus H at the temperature T1 equal to integral from T1 to T2 of Cp of T dt. Okay. Change in enthalpy is just the integral of Cp dt for an ideal gas. Sometimes we can even go a little further in simplification and assume that Cp and Cv are constant. Okay? For constant Cp and Cv, I now see that if we can assume that Cp and Cv are constant, later, much later, we will see that we can call it a cold gas approximation. Okay? Assuming for cases that we can assume Cp and Cv as constants, no longer functions of temperature, maybe for some range of temperature, right? We can assume it not to be constant. Therefore, I see that UT2 minus UT1 equal to just Cv T2 minus T1, right? Upon that, Cv comes out of the integral, and H T2 minus HT1 equal to Cp T2 minus T1. Okay. Now, let me see what one last thing in this chapter, and then maybe next time I'll do some examples. Okay? A polytropic process. I think we addressed it very briefly in one of the lectures. Polytropic process. It's quasi-equilibrium. You remember the quasi-equilibrium, right?
Mhm.
The process is over such a long time that each state can be assumed as equilibrium. It can go to either direction. It's a quasi-equilibrium process denoted by PV to the n to a factor n, or an exponent n. Remember, this is not the number of moles, right? PV to the n equal to constant. That, we call it a polytropic process. The exponent n may take any value, any value from minus infinity to plus infinity. Okay. For example, negative 2.4, right? Or 5.7. It doesn't matter. The relationship between P and V is according to that. Okay. Therefore, I see here that for a process with n equal to 0, process with n equal to 0 gives me P equal to constant. Yes? That's an isobaric process, constant pressure. Isobaric, because the pressure is constant. Isobaric means constant pressure process, therefore I see that on a PV plot. This is my process. Right? I'm going from, let's say, point 1 to point 2. Okay. So for any gas, or even liquid, then a process with n equal plus or minus infinity. If n is infinity, it's a constant volume process. Why is that? V to infinity equal to constant over P. Right? Let's say n is infinity. Okay. That indicates that volume must be constant, because on this plot, on a PV plot, I must have this line, maybe going from point 1 to point 2. Okay. the way to prove it, let us take the dp by dv, right? And you see that it's infinite. Therefore, the line is vertical. Just like dy by dx being infinite, right? Line is vertical and the on the xy coordinate. Okay. Then we see that v is constant. Okay. And the process is called, so P constant isobaric, remember. V constant process is isomeric, process. And then the process for an ideal gas, of course, where n equal to 1. So n equal to 1, n plus 1 is infinity, n 0. But n equal to 1, I see that PV equal to constant. What does that mean?
Ideal gas. Ideal gas.
Is it
Ideal gas. Linear route.
excellent? Does it show that T is constant?
Yeah.
Because PV equal RT, right? And therefore, if PV is constant, therefore RT is constant because PV equal to RT. As a result, temperature is constant. And that means isothermal process, isobaric process, isomeric process, isothermal process. Okay. Very good. Let me see. It's only actually it is 6:15. So we have only 5 minutes. So next lecture I start with going through the entire set of tables. Okay, from A1 to A whatever 24 or something, and then we also look at the English system of the tables because that's also very important. You will be dealing with these tables for the next 6 or 7 weeks. And then I do also some examples. Okay? So take care. I'll see you all on Thursday. Okay? Thank you very much. Don't forget the homework is due tonight.